I was 11 years old when I saw for the first time Neil Armstrong stepping on the moon, and it inspired me to be part of the space program. And this is really a dream come true today.
Tell me about the business, so we're a customer, of course. Tell me about how you're thinking about this as a business.
I think this is terrific. I think commercial space in general, I think is a beginning of a new era, and especially going to the moon and opening it to the commercial companies to compete. I think it's a new era, and it's going to create a new ecosystem in a commercial space, and I think that's wonderful for industry.
That is very cool. Can you tell us more about this humongous lander?
You bet. You've noticed we have the tallest lander.
Welcome, space enthusiasts. In the video you have just seen, Kam Ghaffarian, the co-founder of Intuitive Machines, talks about its ambitions. In the latter part, they discuss the tallest lander, which I'll come back to later in this video. The year 2024 has been characterized by a series of lunar landing attempts, each with its own set of challenges. From mishap before touchdown to lander ending up in upside-down positions, all tilted upon arrival. The path to the moon has been challenging. Today, we focus on Odysseus lander by Intuitive Machines, a marvel of engineering that made it to the moon, though not exactly as planned. Odysseus was equipped with numerous instruments designed for flawless landing. However, a critical mistake was made. The safety interlock of the laser rangefinder was not removed, rendering it effectively useless. Despite this oversight, it's uncertain, in my opinion, whether Odysseus would have achieved a perfect vertical landing even if the instrument had been operational. What do you think? Please share your thought in the comment section. First, let's briefly explore the important instruments and procedure involved in landing. The lunar lander spends 24 hours in low lunar orbit, LLO. In phase 1 of landing, it initiates a deorbit burn, known as a deorbit initialization, DOI, with its train relative navigation camera, TRN, and laser rangefinder sensor, LRFS, oriented downward. The delta position, DPOS, algorithm utilizes surface image to determine the lander's direction of motion by comparing two consecutive images. In the phase 2, starting from 400 meters above the surface, the lunar lander pitches over and navigation is taken over by Hazard Relative Navigation HRN system. This system utilizes an algorithm known as a Hazard Detection and Avoidance HDA, which is tasked with identifying a smooth landing site. In the final descent, within the last 10 meters, there is a risk of brownout, a situation where the engine's exhaust could cause lunar dust to spread, potentially obstructing the camera's view. To mitigate this risk, the DPOS algorithm is turned off. This outlines the planned trajectory. Now let's check the details of mishap, as stated in the briefing by the CEO of the Intuitive Machines. First, the safety interlock of the laser rangefinder was inadvertently left in place, rendering it inoperative. Second, during the final stage of descent, both the horizontal and vertical speeds exceeded the design parameters, even if only slightly off normal. Third, one of the lander's legs caught on the lunar train and broke. As a result, Odysseus flipped over just after touching down and came to rest on an uneven train. Now let's delve into the failure analysis. Before that, if you like, please like this video and subscribe to my YouTube channel. Fortunately, the laser rangefinder had a backup, the Navigation Doppler Radar, NDL, which was on board Odysseus as a payload. Developed to provide precise altitude, speed, and direction data to the guidance, navigation, and control subsystem. The NDL represented a critical backup solution. When the control team discovered the laser rangefinder was inoperative, they postponed the landing procedure by 1 day to substitute the laser rangefinder with the NDL. Having been in development for almost 20 years, the NDL offers accuracy comparable to that of the laser rangefinder. If integrated correctly into the software, this substitution could effectively mitigate the issue caused by the initial human error. Second, the DPoS algorithm is tasked with controlling speed during the first stage of descent, while the hazard detection and avoidance algorithm take over in the second stage. If either of these algorithms fails to function correctly, the landing is jeopardized. A closer examination of the documentation reveals that DPoS is highly sensitive to outliers, with a single mismatch potentially causing failure. In my opinion, the testing conducted for the DPoS algorithm was insufficient for its complexity. Only two types of the tests were performed: terrestrial track test and aerial test using fixed-wing aircraft and helicopters. However, these tests likely did not replicate lunar conditions accurately, leading to a lack of comprehensive performance data. Furthermore, a moon-like scenario test for the entire lander system was notably absent before this mission, contributing to inadequate preparation. Consequently, issues with navigation algorithms and outliers could result in speeds exceeding design specifications. The excessive horizontal speed, in particular, could force Odysseus to veer off course and tilt over. Thirdly, as highlighted in the initial video, this lander stands out as the tallest lunar lander. While tackling the numerous challenges inherent in the returning to the moon after 52 years, adopting a more robust structural design could have been more pragmatic. A sturdy design can provide a buffer against the precise demands of landing algorithms and instrumentation. However, Odysseus' tall structure resulted in a higher center of gravity, increasing its propensity to tilt. When combined with the higher than anticipated vertical and horizontal speeds, this tall design contributed to one of the lander's leg breaking during the tilt over. Although intuitive machines demonstrated precision in the operation of individual subsystems, the mission highlighted a struggle to achieve cohesive performance at the system-wide level. In this new area of the space race, there is an evident tendency to prioritize immediate action over meticulous preparation, underpinned by the belief that lessons learned from failure can, at times, outperform the insights gained from detailed research and testing. Despite the unfortunate tilt marking the final moments of Odysseus lander, the mission stands as a significant advancement in the ongoing quest to deploy lunar landers. Intuitive Machine has two additional lunar landers in development, both designed to be taller and capable of supporting heavier payloads. It is imperative that the valuable lessons learned from Odysseus' mission be applied to ensure success in future missions. I wish Intuitive Machine a successful landing in future missions. See you next time with another space failure analysis.